So first of all, let me thank all of you for being here today. It's a great pleasure, and let me especially thank the member of the jury for having reviewed my PhD. It's been a great honor, and I hope that you will enjoy this PhD defense. Today, I am going to talk about a multi-frequential harmonic balance approach for the simulation of contra-rotating open rotors with an application to aeroelasticity. This work has been done here at CERFACS, supervised by CINNELLA and co-supervised by Frédéric Sicot. Let's first start by quoting the Interpanel Group for Climate Change, who said in 2013 that warming of the climate system is unequivocal, and since the 50s, many of the observed changes are unprecedented over decades to millennia, meaning that global warming is hard to deny and should be accounted for. And one of the reasons of global warming is pollutant emission. And even though the aeronautical industry represents only a small fraction of these pollutant emissions, demanding objectives are set toward this industry. In fact, compared to the 2000 values, the expected 2050 values are expected to be drastically reduced. In fact, according to the European Commission, through the Flypast 2050, the reductions of CO2, NOx, and noise should be reduced by 75%, 80%, and 65% respectively. And actually, one way to reduce certain pollutants is to decrease fuel consumption by increasing the bypass ratio. The bypass ratio is defined as the mass flow ratio of cold air to hot air. The hot air is the air that goes through the core of the system, so through the compressor, combustion, and turbine stages, while the cold air is the air that goes not through this core of the system. And the contra-rotating open rotor is a concept based on an increase of the bypass ratio. In fact, by removing the nacelle, you get the classical propeller system, which is good because it leads to a theoretical infinite cold air mass flow. But the novelty of the core is to add a second rotor, yielding in total a 25% fuel consumption reduction. And also the advantage of the contra-rotating open rotor is that it can yield the transonic Mach number, which makes this concept viable for commercial aviation. The problem is that this is a new kind of engine, so new challenges are raised, among them blade flutter. The flutter is actually a self-excited, self-sustained aeroelastic phenomenon. And this video shows a glider experiencing flutter, and you can see that the wings are oscillating with large amplitude. So you can imagine that if this happened on a CORRE, this blade flutter can lead to failure of the engine. So it should be considered as early as possible in the design chain. And to do so, we use numerical simulation. The numerical methods available for turbomachineries ranges from the lifting line method, which is a simple method as it can be computed within minutes, and is almost used for design purposes as it gives 1D results. On the extreme right-hand side of the figure, you can see that there is also the large decimation, which can be computed in weeks, but is mostly restricted to research purposes, as it is too long to compute. And between those two methods, there is the Reynolds average Navier-Stokes equation, which is a good method because it can be computed in hours, but still provide validation results as it gives 3D results. And you have also the URANS method, which is the unsteady version of the RANS equations, which is mostly used for investigation purposes as it gives unsteady effects. The blade flutter, to simulate the blade flutter, we require to compute the unsteady flow field. So we need either the URANS or the LES method. But what we want is to have a method that gives a time around time that is compatible with industry. And this gives us the place for the harmonic balance. In fact, we want a method that can be computed within hours, but still provide unsteady effects. And this can be achieved using the harmonic balance, which is one of the Fourier-based time methods. So this leads me to my outline. First, in this presentation, I will introduce you the harmonic balance approach, which is the method that will be used in this PhD. Then I will show you the first problem that has been encountered, which is the conditioning of multi-frequential harmonic balance method. And then the second problem is the convergence of this method for wake passing problems. And finally, by solving all these problems, we will apply the method to contra-rotating open rotors. And this yields me to my introduction of the harmonic balance approach, which is divided in 3 parts: the mono-frequential formulation, the multi-frequential formulation, and the scientific bottlenecks associated with this PhD. The harmonic balance approach is an efficient and steady method based on the Fourier transform. In fact, we take 3 hypotheses, like the variable being temporally periodic, the energy being concentrated on a finite number of harmonics n, and the turbulence being fully modeled. And this makes us use of the Fourier transform, of the fact that the variable can be sampled using 2n+1 time instance, and of the Urans equations. Speaking of which, these Urans equations can be written in this simple form. By simply discretizing the problem, we get actually all the samples of the Urans equations. Then, using the inverse Fourier transform matrix, we can express the time samples as a function of the harmonics highlighted in blue here. The fact that the harmonics are independent of time make them out of the time derivative, so that we get actually 2n+1 harmonics equation. And this is the approach followed by Henning and Macmillan et al. But what we want to do is to cast back to the time domain. So we use the Fourier transform matrix so that we can go back to the time domain. And then at the end of the day, we get 2n+1 steady equations, where you can see on the right-hand side that E minus 1 multiplied by E yields the identity matrix. And we get the time derivative operator that is assimilated to a source term. This can be rewritten as this, and you can see that the unsteady problem has been transformed into the solution of 2n+1 steady problems. To test the harmonic balance approach as presented here, we will use a pure 5-harmonic signal whose derivative is known. And then we will test 3 time derivatives. First, a second order finite difference centered derivative, then a fourth order finite difference time derivative, and finally the harmonic balance. And we will show the results as a function of the number of samples and the relative error. And these are the results that we obtain. As you can see, so in red is the second order derivative, in purple the fourth order, and in blue the harmonic balance. And you can see that using only 11 time samples, we get machine precision with the harmonic balance. And actually, 11 time samples is the Shannon minimum sampling to capture a 5-harmonic signal. So the harmonic balance operator seems very efficient on thin spectrum time periodic signals. And this is not the case for the fourth order finite difference approach, which is a good scheme, but still you need to use 100 times more samples to have a larger error. So all in all, the harmonic balance time operator is very efficient, and this is called to be spectral accurate on discrete spectrum signals. The final application of this PhD is to compute the blade flutter of a CORRE, which is actually a multi-frequential problem. In fact, if you consider the blade flutter, which is the vibration of the blade, this involves the aeroelastic frequency, which is denoted FAL. If you consider now the aerodynamics effects occurring on the CORRE, such as wakes and potential effects, you can see that due to the relative velocity difference of the two rotors, these phenomena are correlated to the blade passing frequency. The problem is that the previously presented harmonic balance time operator is mono-frequential. In fact, if you look at the matrix, the inverse Fourier matrix expressed here, you can see that only one angular frequency is considered with its harmonic. But in the almost periodic function framework, a multi-frequential harmonic balance time operator can be defined. In fact, instead of the equations written on the left side of the slide, you can see that the multi-frequential harmonic balance is really close. The inverse Fourier matrix can be used with multiple frequencies, as you can see highlighted here in red. The problem is that the matrix E is not the matrix E minus 1 is not orthogonal, meaning that you need to invert E to get the source term. And this can yield some problems that we will show. And actually, the source term is shown to be real, but numerically, not analytically. The objective of my PhD is to use the multi-frequential harmonic balance approach to compute the flutter boundary of CORRE. And this method has been implemented by several people in the LZCFD code that will be used today. First, Frédéric Sicot implemented the mono-frequential version. Then Guillaume Dufour extended the version to decoupled aeroelasticity. It is not until Thomas Guédéné that developed the multi-frequential implementation in 2013, followed by Benjamin François, who extended the framework to CORRE computations. And finally, my job is to extend the harmonic balance implementation into decoupled aeroelasticity of CORRE. There is actually two main bottlenecks associated with this PhD and with the use of the multi-frequential harmonic balance. The first one is the conditioning of the harmonic balance. If you consider a matrix equation Ax equal b, with A and b being inputs of the problem and x the unknown, by definition we define the condition number as the norm of A multiplied by the norm of A minus 1. And the condition number measures actually the error amplification during the resolution of the matrix equation. In our problem, we can see that we solve the matrix equation. So the condition number of the source term will be problematic. And we choose to focus only on the condition number of E. And looking at the expression of the matrix, you can see that there is two variables, the frequencies and the time samples. And as the frequencies are input of the problem, the only degree of freedom left is the choice of time samples. To highlight the influence of the condition number, let me show you a test case showing you a periodic injection of a sine function into an advection equation code solved using the harmonic balance. If we consider a domain that varies between 0 and Rx, and if we inject a simple sine function into this advection equation code, you can simply know the analytical solution after a translate. In fact, this is just a sine function that has been translated. Solving this problem in the harmonic balance framework using a condition number that is 1 gives us the solution that is superimposed with the analytical solution. Increasing now the condition number yields a bad estimation of the amplitude. Further increasing the condition number gives us even the bad shape of the solution. And finally, it gets worse and worse. The problem is that preliminary studies shows that CORRE blade flutter can yield large condition number, superior to 100 typically. In the literature, several authors have talked about this problem but never really solved it. In fact, Kundot et al. Proposed an algorithm to automatically choose the time samples, but this algorithm can provide large condition number for given frequencies. Ekisi et al., Gopina et al., and Guédéné all use some strategies to modify the condition number, but this yields too high condition number compared to the test case that I have shown you. There is actually a second bottleneck associated with this PhD, which is the convergence of harmonic balance for wake passing problems. To highlight that, I will show you the results of a CORRE low-speed configuration run with the harmonic balance approach and extracted at 75% of the blade height, and I will show you the entropy variation. And what we expect to see is a continuous wake at the interface. There is no reason for the wake to be disturbed at the interface. What we observe is that using only one harmonic for this harmonic balance computation, we can see that we have spurious entropy oscillations. Increasing the number of harmonics kind of solve the problem until we reach a given number of harmonics that's completely solve the problem, which is for this case n equals 4. In the literature, we can see that several compressors, for instance, have been tested by several authors using Fourier-based time method, and we can see that the number of harmonics needed to converge is not the same, so best practice is not relevant. Moreover, a naive approach that aims at increasing the number of harmonics until the solution is reached is not efficient. In fact, for this case, if the n equal 4 is the converged solution, we have just wasted 60% of the CPU time. So this leads me back to my outline, and we'll move on to the conditioning of multi-frequential harmonic balanced methods. I will see two subparts. First, that we have a high condition number possible for core blade flutter problem. And we will propose an algorithm to automatically choose the time instance, such as what I've done Kundert et al., for instance. So to show you the problem of the condition number, I will show you that the condition number computed for arbitrary composed frequency yields several different values of condition number. In fact, we try to build a surface response, a response surface, with arbitrary frequencies. For instance, here we have chosen this couple of frequencies, but it can be any. That ranges between 1 and 10,000 hertz. And we will show the influence of the condition number that varies between 1, which is the theoretical lower bound, and 10, which is the observed stability limit. But do not take this number as it, this figure as it, because it can be any condition number that yields to an instability. So this is the results that we get. We can see first that there is a red line in the middle. This is the infinite condition number line. In fact, if you have FA equal FB, you get a singular matrix. So the condition number is infinite. So we won't look at this line. First remark, we can see that the symmetry of the results indicates that only the ratio of the frequencies matters. In fact, all of these circles shows the same kind of results, so we can say that only the ratio of frequencies matters. Second, we can see that the condition number is minimum for harmonically related frequencies. In fact, the black line denotes the ratio of FB over FA, which is equal to, meaning that FB is the second harmonic of FA. And you can see that for all of these lines too, the condition number is close to the theoretical lower bound, which is 1. One of the problems is that the condition number seems to be maximum when the frequencies are segregated. In fact, you can see this region where FA is largely superior to FB, or FB largely superior to FA. And for these two regions, you can see that the condition number is really high, at least higher than 10. And this holds true for frequencies that are too close from one another. If we compute statistics on this surface response, we can compute the minimum value, the maximum value, the mean value, and the standard deviation. And we can see that the maximum value is just huge. It's 10 at the power 16. You can also see that the mean value is 10 at the power 14, which is just huge, and can prevent the use of such a method for any configuration. In the literature, Ekisi et al. Have tried to oversample the results. Here, for instance, 3 and +1 time instants are used. And you can see that it improves the results, but still it's not satisfying. In fact, you get results that are divided mostly by 3 for all statistics. But still, from the initial values, this is not enough. One other problem is that oversampling gives a negligible improvement considering the additional CPU time and memory cost that it requires. So this solution will be avoided. What we propose is to use an optimization approach where time instants are chosen to minimize the condition number. So this is a minimization problem that we will solve using the LBFGSP framework, which is actually a method that will compute for us the gradient and try to look for the minimum using the gradient and the SCN. And what we need to do is to give an initial good set of time instants to the algorithm to converge. So to take this initial condition, we try to oversample the maximum period. So we take the minimum frequencies and for which corresponds the maximum period. And on this maximum period, we will oversample this period and yielding m subperiods. And for each of these subperiods, we will compute the uniformly sampling time instance. And we get so m sets of time instance where we will compute the condition number. On each of these time instance, we compute the condition number, and the minimum condition number, the set that provides the minimum condition number, is used as an initial guess. And so, to summarize, a good starting point combined with a gradient-based optimization algorithm on the condition number gives our set of time instance. And using this algorithm, we compute back the condition number. This is not a joke. Actually, all values are almost white. And zooming on the color map emphasizes this analysis. In fact, now the values are comprised between 1 and 1.2, which is a condition number that is compatible with any configuration. To ensure that, we compute the statistics. So we show the mean, the max, the mean, and the standard deviation. And we can see that the maximum value is way lower than before, and it's almost close to the lower bound, to the theoretical lower bound. And if you look on the mean value, you can see that it's almost the theoretical lower bound. So the proposed optimization algorithm alleviates the stability issues encountered with arbitrary choice of frequencies. And this is a pre-processing step that takes less than a minute, so it's well, it's a good solution. And this has been published in Journal of Computational Physics in 2013. So this leads me back to my outline, and now we've looked at the first scientific bottleneck, and we will look at the second, which is the convergence of harmonic balance for wake passing problems. So we'll divide this part in two subparts, where we'll show that we have a scattered convergence observed on CORRE configuration. And second, we will try to propose an a priori estimate of the required number of harmonics. So the convergence of harmonic balance will be assessed on three configurations, C1, C2, and C3. The two first one are actually mock-up CORRE configurations, the first one being taken at takeoff or landing, and the second one being at cruise, and these two first configurations are designed by Snecma. The third configuration is the AEPX7, which is a CORRE designed for cruise and designed by Airbus. So the first configuration is the configuration that was used in the introduction, so you will see the same graph. And you can still see that n equal 4 seems to be a good threshold to obtain a continuous wake at the interface. For the second configuration, we can see that it is not n equal 4, but n equal 8 that seems to provide a continuous wake at the interface. Finally, for the third configuration, we can see that n equal 10 is still not sufficient to converge. So back to our three configuration, we can see that the first configuration converges at n equal 4, the second converges at n equal 8, and the second is still not converged at n equal 10. So there is actually two questions that emerges. First, why do these entropy oscillations appear? And second, how to estimate the number of harmonics provided to compute a given configuration. So why do these entropy oscillations appear? Actually, in the front rotor frame of reference, the wake that is shed from the front rotor is seen as steady by the front rotor frame of reference, while this same wake for the rear rotor frame of reference is seen as an unsteady feature due to the relative velocity difference. So at rotor-rotor interface, steady tangential distortion in the front rotor frame of reference are seen unsteady by the rear rotor, and this is the reason why we observe entropy oscillations. The good news is that the tangential distortion at rotor-rotor interface is available using only a steady mixing plane computation. So the idea is to estimate the content of the temporal spectrum using the tangential distortion provided by the steady simulation. So first, we extract the tangential distortion at interface. So this is shown by this graph. And then for each radii, we compute the tangential Fourier transform. This yields us the spectrum of the variables that we compute for each radii. And as said before, the the tangential distortion is becoming an unsteady feature. So the tangential, the azimuthal spectrum is actually equal to the temporal spectrum. So now we want to define an error measure, and we will use the accumulated energy up to a given number of harmonics. Actually, if we take the spectrum that we've computed from the tangential distortion, and if we define a number of harmonics from which we do not compute the solution, we get a resolved part and a non-resolved part. And using this, we can define a truncation error that is classically the red part divided by the whole spectrum, or conversely, the accumulated energy, which is the resolved part squared divided by the whole spectrum squared. And actually, there is a relation between the accumulated energy and the truncation error. So we will use the accumulated energy. At the end, we will show a graph that shows the accumulated energy that varies between 0 and 100%. And we have on the first axis the number of harmonics that varies between 0 and 25. And on the other axis, the radial extent that varies between 0 and 120. 100 is actually the front rotor blade tip, while 0 is actually the front rotor hub. And computing this on the first configuration, we can see that the energy seems to decay fast. Okay, that's good, but what is the threshold of energy required to properly reconstruct a tangential distortion, for instance, here, a wake? So we take a full energy wake, and we reconstruct this wake using varying number of harmonics, varying level of energy. So if we represent this wake using only 50% of the energy, we get the blue wake, which is just bad because you get neither the width nor the deficit of the wake. Using now 90% of the energy improves the reconstruction, but still the width is badly estimated, and the deficit too. Using 99% of the energy, well, it seems that the width and the deficit is properly captured. So on our graph, we will show a line that depicts the energy accumulation up to 99%. And we can see that for this configuration, n equal 4 is needed to capture 99% of the energy on the whole blade radius. For the second configuration, we can see that n equals 7 is needed to capture 99% of the energy. While for the third configuration, n equals 17 is needed, even though n equals 22 might be required to compute the tip vortex too. The good news is that the prediction provided by the a priori estimator is consistent with the observed convergence. In fact, for the first configuration, we had the computation that was converged at n equal 4, while the prediction says n equal 4 too. For the second configuration, we can see that the computation seems to be converged starting at n equal 8, while the prediction says n equals 7. And finally, the last configuration shows to be not converged starting at n equal 10, while the prediction says that n equal 17 might be required. So using the a priori estimator, one can estimate the number of harmonics required to compute a given configuration. And this has been submitted to the Journal of Computational Physics and is actually in minor revisions. This leads me to the final part of the talk, which is the application to contra-rotating open rotors. We will show 3 parts: the steady results, the unsteady rigid results, and the aeroelastic results. So for this part, a low speed configuration is studied. Low speed meaning that inflow Mach number is 0.2, which is a configuration for either takeoff or landing. The steady mixing plane computation is first launched to provide an a priori estimator of the number of harmonics required to compute this configuration. And this steady mixing plane computation is launched with the row scheme with a second order muscle extrapolation, a Spalart-Ayanal Maras one equation turbulence model, a maximum CFR set to 10, and the mesh is meshed using an O4H topology with 129 grid points around the blade, 45 on the pitch, and 181 in the radial extent. And you can see on the right bottom side of the slide, the mesh size. This steady mixing plane simulation is converged starting at 500 iterations. As you can see, the traction coefficient, which is globally the thrust coefficient, is stable starting at 500 iterations, and the number of the number of order of magnitude lost between the starting and 500 iterations is less than 3. So this configuration is converged. Now, knowing that this configuration is converged, we can extract some physical information, such as radial distributions of two variables analyzed at 6 locations. So 2 planes are taken in front of the front rotor, 2 planes between the 2 rotors, and 2 planes after the rear rotor. For each of these planes, we depict the absolute Mach numbers that varies between 0.1 and 0.5. And you can see that the Mach number goes from 0.2, which is the inflow condition, up to 0.4, which yields the thrust because we have an acceleration of the flow field, yielding us the thrust. Now, looking at the angle of the velocity, we can see that just between the 2 rotors, the first rotor has deviated the fluid from about 20 degrees. And the main contribution of the rear rotor is actually to straighten up the flow, as seen here, because at the P6 plane, you can see that the angle of the flow is almost null. Now we can analyze the relative Mach number contours, which shows a smooth subsonic flow field. In fact, pay attention, the CAPI are reversed, meaning that the upper part is the suction side and the lower part is the pressure side. And you can see the classical Mach number, relative Mach number contours for subsonic flow field. This is particularly seen on this slide, which is at 50% of the front rotor blade radius, and this slide. And you can see that between 90% and 95% of the blade height, you can see that we have a low, so this is just here, you can see that we have a low velocity spot, which is actually attributed to the leaving of the rear rotor tip vortex. Now that we have confidence on these steady results, as they provide a good core physical phenomena, we can use the a priori estimator on these steady results to estimate the number of harmonics needed for the harmonic balance. So using our a priori estimator, n equal 4 harmonics should be sufficient, as denoted here. And now computing this configuration with n equal 4 harmonics, we can see that the harmonic balance is able to compute the main unsteady effects. Actually, here you can see the tip vortices shed from the front rotor and that are cut by the rear rotor. So they are now cut by the rear rotor. And you can see that the harmonic balance provides us both the front rotor and rear rotor tip vortices, but as well as the rotor-rotor interactions. So this picture might be odd to you because it's not so well used, but we compute the fluctuation Mach number perceived by the front rotor and the rear rotor. So we compute the unsteady Mach number, which is equal to the temporal Mach number minus the mean Mach number. And you can see that if we look on the left side of the picture, we can observe the potential effect. Now, looking on the right side of the picture, we can see that this Mach number fluctuations shows us the velocity deficits that are attributed to wake passing. And at the end, the harmonic balance is able to reproduce both the potential effect and the effect going downstream, such as wake on this core configuration. So having confidence on this harmonic balance solution, we can now compute the flutter boundary of the front rotor. So we will use 2 modes, which is the second flexion mode and the first torsion mode, as shown here. So we will launch now a multi-frequential harmonic balance simulation using those two modes. To choose the frequencies, we assume on the rear rotor that only the blade passing frequencies will be computed. And we compute when we compute up to 5 blade passing frequencies. On the front rotor frame of reference, we will only compute 4 blade passing frequencies associated to the rear rotor movement, and we will compute 1 aeroelastic frequency. For the rear rotor computation, since the frequencies are harmonically related, this yields a condition number that is the theoretical lower bound. While on the front rotor, we can see that the condition number can vary because the frequencies are not harmonically related. And actually, for the two modes, the condition number varies between 1 and 1,000. And this explains why we had to develop a new algorithm to solve this problem. And actually, using the algorithm developed in this thesis, we can see that the condition number is now between 1 and 1.4, which makes this configuration available for multi-frequential harmonic balance. So now we compute the harmonic response to the vibration of the mode, and we plot that as the local excitation, which is roughly in red we have the unstable part of the mode, and in green the stable part of the mode. You might see that actually integrating these results on the whole blade surface give us two modes that are actually flutter-free, as it gives a positive damping. We can also observe that modes nodal lines are also nodal lines for damping. In fact, for the first torsion mode, on the right side of the picture, you can see that there is an axis around which the mode oscillates, and this axis is actually a line for which the local excitation is null. For the second flexion mode, you can see also that you have the flexion mode that is bending around an axis, and this is shown in black, and this is also a line where the local excitation is null. Another interesting thing is that also aerodynamic variation lines are also nodal lines for the damping. In fact, the black line depicts the end of the acceleration on the suction side, and this line is also a line where the where the damping varies and changes from a positive to a non-stable, from a stable to an unstable part. So now that we've computed the harmonic balance, the multi-frequential harmonic balance for CORRE blade flutter, we will now try to estimate the cost of this method compared to classical methods. So this is just a tentative, and it is hard to do because there is no right way to do that, so I'll try. We can split the problem into degrees of freedom. In fact, each time operator has several degrees of freedom. For instance, for the DTS, which is the time accurate simulation, we need to parameterize the time step, the number of iterations, the number of time steps, meaning the number of time periods to bypass the transient, and also if we use the phase lag or the 360 approach. And on the harmonic balance side, we can see that we have only 3 degrees of freedom, as we need to compute the number of harmonics, the number of iteration, and we are always phase lag, so we cannot have a 360 simulation. And actually, there are facts in our ELSA implementation of the harmonic balance. For a rotor stator configuration, we have observed that n equal 4 is needed to capture the unsteady outlet mass flow rate, and this yields a gain of 5 compared to the phase lag DTS. While for an isolated aeroelastic configuration, n equal 1 is enough to capture the damping. And for this particular configuration, we have a gain that varies between 3 and 10 compared to the phase lag DTS, depending on the case considered, meaning the operating point and the EBPA, the interblade phase angle. Sorry. And these two results are published as SICOT et al. In Journal of Turbomachinery and as SICOT et al. In AIR. And actually, these figures, a gain of 5 and a gain between 3 and 10, can be explained because the DTS requires 20 points, roughly, to converge, while the harmonic balance only requires 3 points, which is the Shannon minimum of sampling to capture one frequency. And this yields a gain for the harmonic balance, which is 6.6. So what we can estimate is that now, looking at our problem of CORRE blade flutter, we can say that the 360-degree DTS is required, as phase lag DTS is not applicable with multiple frequencies, non-harmonically related. And in the opposite, the harmonic balance multi-frequential can be used with multiple frequencies, so we can use both the blade passing frequency and the aeroelastic frequencies. And the cost scales with the number of additional frequencies. So at the end of the day, the gain can be equal to 7, which is 6.6, or between 5 and 3 and 10. Well, this is one figure, multiplied by the mean number of blades, because 7 is the temporal operator comparison, and the mean number of blades is actually the mesh size reduction attributed to the phase lag approach. So for our CORRE configuration, this gives an expected gain of 70, which is roughly 2 orders of magnitude. But again, the DTS 360-degree has never been launched, so this is just an estimation. So this yields me back to the conclusion. So first conclusion on the conditioning of multi-frequential harmonic balance methods. We can say that the presented optimization algorithms allows to minimize the condition number of the multi-frequential harmonic balance approach by properly choosing the time instance. It shows to be both robust and accurate, as it gives a condition number close to the theoretical lower bound for almost all choice of frequencies. And this work has been published in Journal of Computational Physics. Now, on the convergence of harmonic balance approaches for wave passing problem, we can say that the number of harmonics required to compute a given CORRE configuration has been estimated. And this a priori estimator is based on an affordable mixing plane simulation. The prediction for 3 CORRE configurations shows to be both accurate, and this allows to skip the naive approach iterative. And this work has been recently accepted with minor revisions in Journal of Computational Physics. And finally, the kind of merged conclusion on the aeroelasticity of CORRE. We can say that the multi-frequential harmonic balance method with both the optimization algorithm and the a priori estimator allow to compute the blade flutter response of a low-speed CORRE, which was not available with the DTS. And this proved the maturity and robustness of the multi-frequential harmonic balance approach. So now I have 2 perspectives. First, the installed CORRE configurations. During this PhD, other CORRE configurations have been computed too, and one of them was an installed CORRE configuration. And the advantage of the a priori estimator is that we can launch the a priori estimator on such a configuration. And actually, this a priori estimator shows that 300 harmonics are required to compute this configuration. So this highlights the power of the a priori estimator as it helps the decision making, meaning that for this configuration, we never launched the harmonic balance computation, of course. And there is another perspective toward accurate aeroelastic simulations of CORRE, because I have shown you some results on CORRE aeroelasticity, but these results were only for the front rotor, so the rear rotor needs to be assessed. But also, I have partially assessed the choice of the multi-frequential frequencies. So this is something that needs to be done. And also, we need to take into account the influence of the vibration of the blade on the aerodynamic of the opposite rotor, and also the influence back to the vibrating blade. So thank you very much.